Ampere's circuital law, and I hope all of you have studied what is Stokes theorem. So Ampere's circuital law, because we will need it. Stokes theorem will be needed. So in Ampere's circuital law, I will do it for vacuum. Okay, let me write down its definition that you have done your plus 2 class. According to it, the line integration, the line integration of magnetic flux density over a closed path in vacuum is always equal to mu naught times the current threaded by the closed path. This was the definition, and its mathematical form was this: integration B dot dl over closed path is equal to mu naught I. So where C is any closed path. So it's proof. You did not prove it in plus 2 class. So suppose this is any closed path. This is a closed path. This is a current carrying conductor. The current passing through the conductor is I. Okay, so this is a closed path. Let me tell you, this is sub figure. This is sub figure. So this is a closed path, and in this closed path, this is the area that the closed path will cover. This is the area. So if I move like this on the closed path, this will be the area. Let us say this area is S. Please remember, you should remember this. For this closed path C is closed while the area S inside the closed path is open. Are you, I guess you should be clear about this, because if you do not make yourself clear about this fact, you will not be able to understand it. Okay, now we know that every current carrying conductor is a source of magnetic field. We know this. Every current carrying conductor, this is Oersted experiment, produces magnetic field. We know this. And for a straight conductor, the magnetic field lines are circular. So let me draw the magnetic field lines. I will use, let me use some different color of the pen for magnetic field lines. Let it be black. So magnetic field lines will be circular like this. The magnetic field will be everywhere, of course, and the sense of the magnetic fields, it will be found using right hand thumb rule. Is it okay? So if it is, if the current is upward, then the, so let me draw the magnetic field lines. I will use, let me use, hello, can you,
Guruji,
yes, boliye.
the 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 side direction of the magnetic field line changing always.
If the current is, let us see, from down to up, then the sense of magnetic field will be just I have shown. Let us say current is like this, it is up to down, then the magnetic field lines will be circular, but
So
the sense will be opposite, like this.
changing.
Are you clear now?
So if the current is in upward direction, the direction of magnetic field at that point is perpendicular to the plane of the paper inwards.
Direction will be, if it will be in the direction of magnetic field will be perpendicular to the plane of paper at this point. This point,
Yes, sir.
let us say P1,
Now,
this point
this
P2. Here the magnetic field
direction
is
of
entering, so it will be like this. Here the magnetic field is coming out, it will be like this. But what about these points? Let us say this point is P3 and this point is P4. What about these points? Here the magnetic field will be parallel to the plane of paper, like this and like this. So this statement cannot be made. Is it okay?
okay. So this means the direction of the magnetic field line always changing.
Yeah, in a circle, all directions are covered.
Yes, all direction. Okay. Clear.
Okay. So what we will do, we will divide this closed path into small segments like this. So I will take some point O. I will draw a dotted line here, and I will draw a dotted line here. So this small segment will have length dl, and the angle subtended by this small segment will be d theta 1. Yeah, the, let us say d, this segment is dli, and this angle is dli. Is it okay? हाँ जी,
Sir, how this angle is
मैं
made?
तो
Like
11 बजे मिलूंगा, 11 बजे. हाँ जी, yes.
how this angle is made?
This angle is something, there is always a, look, this is any point O, this is some segment of the closed path. This
Okay.
has
So the
dli.
DL
This
is
angle I
making the
have
angle.
assumed theta I.
Okay. DL
I will,
making the angle.
I am assuming this angle d theta I.
Okay. No,
Even
the line was not clear.
okay. This is
Yes.
now, I will make the bold lines slightly thicker. Now I
Yes.
think it will be clear. Suppose the distance between O and the segment DLI is Ri, let us say. Would you agree with me that d theta I is will be equal to DLI upon Ri? Is it okay?
Yes. Simple formula. Yeah.
Yes, sir.
Because angle is equal to arc upon radius. Okay. Now, will you agree that if I divide this whole closed path into large number of segments, let us say here, let us say here, like this, then summation of all such angles d theta I, suppose there are n segments, so I will go from 1 to n. Would you agree that it should be 2 pi radian?
Yes, sir. It will
Yes,
be
sir. It will
60 बन
complete
जाएगा वो.
Yes, sir.
2 pi.
Yes.
Okay. Second, this is a trivial thing. Okay. So I will write this as equation number 1. Would you agree that Bi is equal to magnetic induction at DLI due to current? Due to current. So for that you have to recall your school physics formula. What was the formula for magnetic field due to a state conductor? It was, yes, it was mu naught upon
I
4 pi. It was 2I upon R. Is it okay?
Yes.
Yes, sir.
Okay, now I would use the symbol Ri because there is not one segment. This is one of the segment. Actually, there are many segments. This is also a segment. This is also a segment. This is also a segment. I have divided closed path into large number of segments. So for each segment, some segments, for example, this is the farthest segment from O, and this is the nearest segment from O. So Ri is changing from place to place. So for different segments, the direction and the magnitude of magnetic field will be different. Is it okay?
Okay.
So I am using Bi is equal to Ri. Next, I have already drawn the direction of magnetic field lines here. So this is drawn separately. What would you interpret? Suppose this point is P1. Let us say this point is P1. what would you interpret at P1? What is happening? What is the angle between direction of DLI and magnetic field? Please tell me. The magnetic field should be seen from this place and DLI should be seen from this place. What is the angle between these two?
So 0.
0 degree. Okay. So therefore, B vector I dot DL vector I will be equal to BI. Yes, it will be equal to BI DLI cos of 0 degree. Is it okay?
Yes, sir.
That will be equal to, rather I will write in the bracket, for all values of I. This will be true for every segment. And BI is equal to what? It is mu naught upon 4 pi 2I upon RI, and DLI.
Excuse me, sir.
Yes.
Sir, you've written magnetic induction at DLI due to current is mu naught upon 4 pi into 2I. So, how's that 2I?
If you can recall magnetic field due to a state conductor, its formula was mu naught I
Mu naught
upon
4 pi
2
d sin
pi
theta
r.
plus sin theta 2.
Okay, sir.
So why I have written it like this?
Yes.
Because we know that the value of mu naught upon 4 pi is
Okay,
simply
sir.
10 raised to power minus 7. I think that it will be helpful for numericals. It was
Yes, sir.
Tesla meter per ampere. That is why instead of 2 pi r, I wrote here 4 pi and I wrote here 2i.
Okay, sir.
That will be helpful in numericals.
Yes, sir.
Is it okay? So I want to change the page. Now, what is DLI upon this RI? It will be simply, now I can cut it.
D
It
theta
will
I.
be,
D theta.
it will be mu naught I upon 2 pi into D theta I.
Theta I.
Is it okay? This is equation number 2. I want to
Okay.
move to next page.
Next.
So wait for a while, let the new page load. So new page has loaded. So BI dot DLI, I have proved it to be mu naught upon 2 pi and I and d theta I. Now let us prove Ampere circuital law. Left hand side of the Ampere circuital law, it was integration over closed path C B dot DLI. Now we have divided this closed path C into large number of segments. So this expression is equivalent to I going from 1 to n. It will be B I D L I vector. This was my equation number 2. So put the value of equation number, yes, 2 in this, then progressively it can be written as summation of her I, yes, n, I going from 1 to n, it was mu naught I upon 2 pi, and it was d theta I. Mu naught I and 2 pi being constants are taken out of integration. So it will be mu naught I upon 2 pi. It will be summation in this case. This will be summation I going from 1 to n d theta I. What do you know about this value? What is this summation?
2 pi.
It is 2 pi. So this will cancel with
2 pi.
this 2 pi.
Okay.
So
Mu
therefore,
naught I.
it will be equal to mu naught I. Hence, I have to attend a call, please. बोलो, मैं क्लास में हूँ बेटा, 11 बजे के बाद बात करना, ओके? Okay, students, I think hence we have proved that integration of B dot DLI is equal to mu naught I. Is it okay?
Yes.
Ampere circuital law is proved. So next article that I am going to do now, it is Ampere circuital law in vacuum for differential form. So differential form of Ampere's circuital law.
Sir, this integration is about the closed path or open surface means.
This is always applicable to closed path. This is a, please remember, this variable dl will clarify. What is this dl? Is it length or area or volume?
Length.
So it is
Then
so it is a one dimensional integration. It is over the length. It is on the closed path. Any other question?
ਸਰ
Yeah.
ਸਰ ਜਿਹੜਾ ਤੁਸੀਂ bi.dl ਵੈਕਟਰ ਆਈ ਕੀਤਾ ਸਰ ਉਹ cos 0 ਕਿੱਦਾਂ ਆਇਆ ਸਰ ਉੱਥੇ
cos 0 इसलिए आया बेटा, सपोज करो मैं यहीं पे पिछले पेज पे नहीं जाता. सपोज दिस इज द करंट I. What will be the, let us say, what will be the direction of magnetic flux density at this point P? Please tell me. How will you find it?
Area.
You will use right hand thumb rule.
Sir, inside.
ਯੈਸ ਸਰ
yes sir.
So you will say that magnetic field line is a closed loop and it will be centered at the conductor, and the sense of the magnetic field will be like this. And at any point where you want to find the direction of magnetic field, what will you do? You will draw a tangent. If you draw tangent at point P, what will be the direction of the tangent?
Inside the plane of the paper.
It is inside the plane of the paper, normally inside the plane of paper. And the closed path was also inside. The direction of dl at this place was also inside. So dl and b are in the same direction independent of the position of point P. If you draw point P here, then b and dl will be in the same direction here. So theta is not that theta which I showed for segments. This angle is something phi. You can use this angle to be phi. So b dot dl, kindly do not expand it by b dl cos theta. Expand it by b dl cos phi. Because theta, I have already used theta angle symbol. I have used theta symbol here. So
This
here
is
the
obviously parallel.
angle symbol should be something different. Use something phi. Then you will not be confused.
Excuse me, sir.
Yeah, please.
Sir, how did you find the direction of DL? Can you please explain again?
The direction of DL very simple. It is either clockwise or anti-clockwise. You want to cover a closed path. You have only two options. Will you agree?
Anti-clockwise from upper
Yes,
side.
sir.
ਯੈਸ ਸਰ ਯੈਸ
You can cover a closed path only in two senses,
Yes,
either
sir.
clockwise or anti-clockwise.
Yes.
Is it okay? So logically, that angle can have two values. Either if you are moving
180 or 0.
or
180.
very good, very good. This will be only 180 and 0. Now we have a choice. How we want to cover the path. We have a choice. So we are mature enough and we will cover the path in the same sense in which the field lines are moving. For example, if the current is moving upward, then we will cover the path. This is anti-clockwise. If the current would have been down, then we would have covered the same path in this sense.
In the anti-clockwise.
So that the angle is always 0 degree. I
Yes.
think you are satisfied now.
Yes,
Yes,
sir.
sir.
ਯੈਸ ਸਰ ਯੈਸ
That direction is parallel with current conductor.
Yeah, of course. Yeah, that is what I wanted to say. In fact, I used it. Is it okay?
Yes.
ਯੈਸ ਸਰ
Okay, let me now draw the differential form of Ampere circuital law. I need more space, so rather I will shift to new page.
So please wait for a second.
Okay. Please say when I want to move to next page. Is it okay?
Excuse me, sir.
Yeah, please.
So when will you take the class for the doubts for the laser chapter? Because our only one class has been there regarding
Okay,
this.
okay. Today I have a tutorial at 3 p.m. What is your schedule of your class?
Till 3 p.m. So wait.
Check. You can join that tutorial.
Sir, we have a mentoring class at that time.
Okay,
Guruji,
at
is there any practical that we can perform at home?
no, this is a BTech class, and it is unfortunate that we are facing COVID-19. All the experiments require equipments which are not available in your home. These
Okay, Guruji.
equipments are expensive, so you cannot assemble any equipment at home. This I feel very sorry for that, but it is not in my control, dear.
Okay, Guruji.
Okay. Okay. Next is now I would rather draw the same diagram because Ampere circuital law in integral form we have proved. So this was a state conductor. Okay. Now we want more complexity. Okay. So please remember this is now many conductors. Some of them might be carrying current in a downward direction. This you have never learned in your school physics. Instead of that, we can also have a thick conductor, let us say, and it is not necessary to be straight. Let us say it's like this. So this is a thick conductor. So from here the current is I1, here the current is I2, here the current is I3, and here the current is, let us say, IT. Thick IT stands for thick conductor, and some current is going out, some current is going in. So now this is a very complex situation. This is a closed path. See again, what is the difference? The difference is that in the integral form I took just one state conductor. Here I am taking many state conductors, and even I am taking a thick rod. First of all, that you should remember that, let me change the pen color, that this area, please remember, this area will be now divided into many parts. This is the shaded area of the plane of the coil. Sorry, it's not a coil, it's a closed path. So I will, let us say, draw a small, let me change again the color of the pen. Let me draw a small closed path, small open surface. This is small open surface. So this open surface is DSI. Now, if I draw small open surface here, let us say this small open surface is DSI dash. Now, please remember that current passing through this surface and this surface is not same. Would you agree?
Yes, sir.
Yes, sir.
Yes,
sir.
Yes, sir.
Okay, that's good thing. Secondly, charge can be divided over volume. Is it true?
Divide means it can be split.
Charge, suppose this is a body.
Yes, sir.
This body has this portion, total charge on the body is this. So the charge can be present on the surface as well as within the body. Is it true? In
Yes,
general, the
sir.
answer is yes. Is it okay?
yes, sir.
In general, the answer is yes. So the variation of charge can be seen over length, over area, over volume. That is why you have line charge density, surface charge density, and volume charge density. Am I
Charge means electrons, no?
Charge means it could be protons also, dear. Any charged particle.
Yes, sir. We agree.
You
Okay,
agree.
okay, proton too.
Okay. Now, can you give similar kind of statement? Can you give similar kind of statement for current? Okay, current can also be divided over volume. The answer is obviously no.
No, sir.
Current
Surface only. Surface.
current always changes from area. So we have only one current density. Please remember, we have three charge densities: line, surface, volume. But current density is only one, that is current per unit area. So the current density here will be different and current density here will be different. Is it okay?
Yes, yes.
Okay. So let the total current passing through this small surface is di. Is it okay? Now you know what is di. It is j vector dot ds
DSI.
vector. Is it
Yes,
okay?
sir.
In general, I
Yes,
am
sir.
taking now ds. In general, I am now taking ds. It means this ds could be this also. It could be this also.
Also.
Is it okay? What I want to find the total current. Please remember, the sum of the currents of all these, let us say, all these currents, when added, the total current comes out to be I. Please tell me, how can I find this I?
Integration.
Integration. It will be integration of di. Please tell me, should this integration be done over the boundary of the closed path or over the area of the closed path, which is shaded red?
Area.
Area.
Very good. Because I have just completed that current divides over only area.
Area.
So I
Yes,
would
sir.
show, I would use one integration sign or two.
So 2.
2.
Very good. Now please see. In case of one integration sign, I put this circle. That means the path was closed. Am I allowed to use circular sign here? Yes
No.
or no?
Yes, sir.
No.
No, sir.
No, sir.
No,
Answer
sir.
sir.
is no, because
No,
this
sir.
area which is shaded red,
Open
it
surface.
is open area.
Open area. Yes. Obviously. Open.
If you do not understand the figure, forget that you will be understanding the article. Is it okay? So I am stressing a lot on this figure. So this will be equal to
Open area.
Volume is also open, no, sir?
volume is always open. Area can sometimes be open, sometimes be closed. But for this particular example of Ampere circuital law, the area is open.
Open.
ਸਰ ਤੁਸੀਂ ਸੀ ਵੀ ਲਿਖਿਆ ਤੁਸੀਂ ਓਪਨ ਵੀ ਕਰ ਰਹੇ ਹੋ ਸਰ ਆ ਕੀ ਗੱਲ
C is for closed path.
ਸਰ ਇਹ ਓਪਨ ਏਰੀਆ ਕਿਵੇਂ ਦੁਬਾਰਾ ਦੱਸੋ ਇੱਕ ਵਾਰੀ
Beta, in case of open area, you put some volume inside open area. It can be taken out. इसको चोर चोरी कर सकते हैं. उस सरफेस को हम ओपन सरफेस कहते हैं जिसके अंदर रखी हुई चीज की चोरी हो सकती है. ये थाली होगी ना, इसके ऊपर चपाती रख दो, कोई भी उठा के ले जाएगा. तो ये ओपन एरिया है. Is it okay? इससे अच्छी एग्जांपल मैं नहीं दे सकता. Wherever please somebody was saying that you are also writing C. Please remember, I am writing C. C stands for closed path, and this red area, this is written by symbol S. It is open surface. When I write C, it means you are moving only on the boundary, which is written by shown by a black line. And when I use S, then it is by red region. Is it okay?
sir.
So this is my equation number 1. Now by Stokes theorem, now it is time for you to tell me the answer. By Stokes theorem, please, I am writing left side of the Stokes theorem. Okay, please tell me. B dot dl over closed path, it should be
So del cross.
Del cross A. Del cross B.
yes, it should be del cross B
Dot DS.
dot ds.
Dot ds.
Integration will change from C to S, from closed to open. This is equation 2. Put both of these
ਸਰ ਡੈਲ
values.
ਕ੍ਰੋਸ ਵੀ ਬ੍ਰੈਕਟ ਚ ਆਊਗਾ.
Okay, thank you. Put both of these equations in integral form of Ampere circuital law. The mic of some student is noisy. Kindly mute. So it will be, what was Ampere circuital law? B dot dl is equal to mu naught I. Now I am going to put the value of this from second, and I am going to put the value of this from third. So this will become double integration del cross B dot ds. It will be mu 0 double integration del, sorry, it was j dot ds. So I can bring this right side on the left hand side, and let me add new page. When I bring right hand side to the left hand side, this will become double integration. I will take it to be common. It will be del cross B minus mu naught J dot ds is equal to 0.
सर एक बार पिछला पेज दिखा देना, लास्ट स्लाइड नोट नहीं कर पाया मैं.
Okay, okay.
डन सर.
हमारे पास अब डाइवर्जेंस क्रॉस बी माइनस म्यू नॉट जे आएगा, उसको सर हम इक्वल टू 0 पुट कर देंगे अब.
वो हो ही बेटा. I have brought everything on the right hand side to the left hand side. What will be the left in the right hand side? Please tell me.
फिर ऐसे हो तो फिर वहां पर तो 0 आ जाएगा. फिर जो मतलब जो सारा जो चीज है जो डीएस के साथ मल्टीप्लाई हो रहा है अब सर, उसे भी हम 0 के
हाँ वो 0 हो जाएगा.
सिंपल अलजेब्रा सर.
हाँ, this is the logic will be same. Suppose I have taken the closed path like this. My answer is 0. Suppose I take the closed path smaller. What will be the answer? 0. And if I take the closed path this much bigger, what will be the answer? 0. What is
independent of size?
What is the difference that when I am changing this, it is equivalent to changing the limits of integration.
Limits.
Yes, sir.
And only one such function satisfies the property that when you change the limits, you always get the answer 0. This is satisfied only by 0 function. So everything inside the round bracket, which is called integrand, it has to be 0. So del cross B minus mu naught J has to be 0. So this becomes del cross B is equal to mu
Guruji,
naught J.
we do not have to give any explanation.
You have to write that one line. I wrote that line on my open board when I used it for the first time. Now I am not writing it. You have to write it.
Okay.
This is called Ampere's circuital law, differential form. If you have any problem, you can ask me. This is differential form.
सर मैक्सवेल इक्वेशन है सर.
हाँ जी. Somebody has asked, is it a Maxwell's equation? So I would give the answer to this question, of course, but I will be happy if somebody tells the answer yes or no. Somebody dares to say yes or no. Is it Maxwell's equation?
Yes sir.
Yes, sir.
Answer is no, sir.
No.
No sir. Yes,
It is not Maxwell equation, because you know how many times you did the Ampere circuital law in your school level physics? 1 time or 2 times?
I actually read this theory.
So 2 times.
2 times. First in magnetic field chapter, second time in which chapter?
EM
EM waves. Okay. In EM waves, Maxwell said to us that this law, this is the differential form, and this is the integral form. B dot dl is equal to mu naught I. Both of these are same things. This is in integral form and this is in differential form. And Maxwell told us that this equation is not correct. You know this?
Yes, sir.
Yes sir.
And Maxwell corrected it to which form?
Displacement
Integration
current.
B dot dl is equal to mu naught I plus
D.
ID. That ID was displacement current.
current.
Yes, sir.
That
Yes, sir.
was
Yes.
that was correct Ampere circuital law. We would
Yes.
rather
Yes, sir.
call that as Maxwell equation. We will not call this as Maxwell equation.
Yes, sir.
If
Sir,
in the, yes, please ask.
सर J वेक्टर सर करंट डेंसिटी है
Which one?
सर जरा ही लिखा I is
हाँ,
equal to
I by
J.
A current density है. Oh, current density नहीं, sorry.
This is called displacement current.
No,
Sir,
no,
J
sir.
पूछ रहा है सर.
Simple, sir.
J dot
J is
ds.
current
Current
density.
density.
J is current
I
density.
by A.
I by A. Okay, sir.
Please
Okay.
do not call it as I by A. Please remember.
फॉर्मूला समझ लिया.
हाँ, please remember J is equal to I by A only when, yes, ds vector and J vector are in same direction. Only then this is true. If they make some angle, then you can write J is equal to I upon A cos theta. That is the correct answer. If current and area vector are not in the same direction, then the correct formula is this: J is equal to I upon A cos theta. Please remember, this is the best answer to this. You are not habitual of using this cos theta, but actually it should be used. In school level physics, we do not tell this thing to you.
I equals to J dot A भी.
सर J ये करंट डेंसिटी है ना?
हाँ हाँ बिल्कुल है. It is a current density. Any other question? Okay, I am going to add new page. Okay, next is yeah, please. What is asking? What you have asked? Please tell me what you asked. पिछला page. Okay.
Yes, sir. Yes.
When you have noted it down, then please tell me. I will go to the next page.
Excuse me, sir.
Yeah, please.
सर जो आपने ये इंटीग्रल फॉर्म और डिफरेंशियल फॉर्म बताया, इसमें डिफरेंस क्या है?
किसमें?
सर जो आपने एम्पीरियल सर्किटल लॉ बताया डिफरेंशियल फॉर्म में और इंटीग्रल फॉर्म में.
Okay, I would rather want to ask a question from you to give the answer to this question, so that I would check that whether you understand these things easily or not. Okay, please tell me what is the difference between integration and differentiation. What is the difference between instantaneous velocity and average velocity?
सर इंस्टेंटेनियस एट अ टाइम एट अ मतलब कि एक स्पॉट पे, और एवरेज हो गया पूरा स्टार्टिंग टू एंडिंग तक का मिला के.
That is the answer here also. In case of integral form, it is the average behavior. In case of differential form, it is the behavior of the magnetic field at a given point in the region. This is the difference.
That means instantaneous.
Equation, yeah, equation 3 is a point equation. Equation 4 is a region equation.
Okay. So fourth integral form.
Somebody's mic is very noisy. Kindly mute. Yes, now.
Sir, instantaneous differential form वाला है.
Yeah. नहीं. That was I just took example, beta. Instantaneous
Yes.
की बजाय you will use here the word point.
At a point, yes, sir.
This is the behavior of magnetic flux density at a point where the current is J. Current density is J. This is the behavior of magnetic. Sorry, I forgot to put a dot here. This is the behavior of magnetic flux density over a closed path where the total current threaded is I. So this is, you can say this is a macroscopic equation. This is a microscopic equation.
Okay, sir. Thank you, sir.
Any other question?
No, sir.
What is your next class? Which subject?
Sir, ED lecture.
ED lecture. Okay, we have to leave it at exact time. Okay, next is I have 9 minutes remaining. So next is limitation of Ampere's circuital law in vacuum. Limitation of Ampere's circuital law. You know what limitation I am going to discuss now?
Displacement current.
No, where it was not applicable.
सर
Inside the
Capacitance symmetry is
capacitor.
not available.
कैपेसिटर में सर जो मैक्सवेल ने क्वेश्चन दी थी
हाँ नहीं नहीं वो तो दी थी
When symmetry is not available.
कैपेसिटर में ही होगा सर वैक्यूम में वैक्यूम सर
सर ये जो ला है सर ये बस वैलिड है स्टैटिक करंट्स के लिए सर
Freeze.
Sir is not audible.
Flickering screen.
Okay, sorry, there was a connection breakup. Do you know what is steady current?
Yes, sir.
करंट सेम रहता है
No,
सर that does not change
Same,
is
sir.
insensitive with time
Very good. Steady current is that current in which the value of charge density does not change with time. Okay, we will be doing that. What is steady current and how whenever there is a capacitor in a current, then you cannot have this law applicable. Let me do that. So we have proved this. We know that just now we have proved that we know that del cross B is equal to mu naught J vector. Let us say this is equation number 1. Take curl on both sides. So left hand side will become del cross B, and right hand side, sorry, do not take curl, sorry, take divergence on both sides. Take divergence on both sides. Left hand side will become this and right hand side will become this. We know this thing. We know this is a scalar triple product. A dot B cross C is equal to, we know this. This is AX, AY, AZ, BX, BY, BZ, CX, CY, CZ. This is the volume of the parallelepiped formed by three vectors A, B, and C. I guess you know this. And you also see if I put B vector is equal to A vector, then what is going to happen? This second row will become identical with the first row, and
Zero.
obviously it will become 0. So now you can see here this first vector is del, second vector is also del. What should be the answer of this scalar triple product on the left? Zero should be there. Therefore 0 will be equal to mu naught into del dot J, and you can divide both sides with mu naught. You will get del dot J is equal to 0. Therefore I can say, therefore equation 1 is valid only for those currents whose divergence is 0. Current densities, I would rather use the word current densities, because J is in real sense it is not current, it is current density. So equation 1 is valid only for those currents for which divergence is 0. Such currents are called steady current. Such current is called steady current.
सर सोलेनोइडल शेप होएगी सर ਉਹਦੀ
Very good. It will be solenoidal shape. Means such a current will start and then it end up. It will not have any starting point and end current. That current will start from a point and it will end up for a point. Is it okay? What was your name here? Jobanpreet, you have made my discussion 10% easier. Now I can very easily explain the things to the students. So please remember, such a kind where the divergence is 0, such a vector is called solenoidal vector, and for such a vector, the vector representation of such a vector is that it will not have any starting point and end point. Such a vector will always have closed loop. Just I have shown here. Let me now show what is not possible. Steady current की property बताने जा रहा हूं. Now see, you have a capacitor here. Sorry, I will rather show it bigger. You know that there is a, let us say there are two plates of a capacitor, and you have a resistance, you have a battery. Can I ask you a question? Have you studied the working of a cell?
Yes, sir.
Okay, if I insert the key, will the current flow from the positive terminal? Answer is yes or no?
Yes.
Yes, sir.
Conventionally, yes.
Yes, sir.
Will this current pass through resistance R?
Yes, sir.
Will this go here? Yes. Will
Yes,
this
sir.
go here? And this plate will get positive charged. Will the current
Yes.
flow from this plate P1 to P2? Please
No.
tell.
No,
No.
sir.
No.
No,
Answer
sir.
is no here. Will the current flow here? Yes.
Yes.
Here. Here.
Yes.
Here. Within the cell, will the current flow?
Of course, yes.
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 So the answer is yes everywhere. Where the answer is no.
Inside the capacitor.
Inside capacitor.
Inside the capacitor current is no. Will it make solenoidal?
No, sir.
Will it have starting or end point or no? Will it be a closed current path or not?
Not.
No, sir.
No. So whether Ampere circuital law will be applicable to this circuit?
No, sir.
No.
No, sir.
This is something which you have done very easily. In +2 class, I think you were given an explanation like this. Please acknowledge this. Your teacher told you that you take one closed path here, C1, one closed path here, C2. Then you say integration B dot dl is mu naught I for C1, but it is 0 for C2. This is not possible.
Yes, sir.
But you have to remember these things. Most of the students are unsatisfied with this explanation. But here, everybody should be satisfied. Is it okay? So I will stop here. So I will conclude this discussion that Ampere circuital law that we have just derived in this lecture is applicable only for steady currents, and steady currents are produced only in the circuits in which the capacitor is missing.
सर एक बार पिछली स्लाइड दिखा दीजिएगा सर.
Okay. Please remember you have a next lecture, so I will leave